Hello. Let's talk about the staircase problem. The basic gist of this problem is that you're a person sitting at the bottom of a staircase with a certain number of stairs ahead of you. And we're interested in counting the distinct ways that you can climb this staircase, where the difference would be is you could take a step length of one, then maybe two, maybe back to one, and then maybe finish the rest with 1, 1, 1, 1, 1, things like that. I'm going to eventually cover three possible solutions to this problem using Python. The first one, which is a relatively simple, maybe even elegant solution, is the recursive solution. That's the solution that we'll be covering in this video here. The next one after that, I really don't have a name for it other than calling it the backwards lookup solution. And the final one that I have is a combinatorics based solution. So to move forward, I want to talk about a very specific and simple example. How many distinct ways are there to climb 4 steps when taking either a step 1 at a time or a leap 2 at a time? I labeled the step and the leap just to make the verbiage easier when communicating that. Anyways, I'm going to jump down to my surface and do a little explanation of this simple example here. I'll see you then. Ways of climbing the staircase with 4 steps when either taking step, which has a length of 1, come back here, or a leap, which has a length of 2. Now, when I think about this problem, I think about it as a series of decisions that we have to make. And anytime when I think about decisions, I naturally think about a tree. So I'm going to set up a tree diagram. We start off with 4 steps ahead of us, and the decision we have to make is to either take a step or a leap. If I take a step, which just has a length of 1, that would mean after we take that step, we have 3 steps ahead of us. If I take a leap, which is a length of 2, that would mean that we have 2 steps ahead of us after that. Now, looking at this 3, again, I can make that decision. We can either take a step or a leap. If we step, that would go from 3 to 2, leap 3 to 1. From this 2, we could step, we could leap. If I step, that would give us 1. If we leap, that would be 0. Now 0, that would indicate that we reached the top of the staircase, and that would indicate a distinct way that we could climb the staircase. From this 1, we can still continue. We can either take a step. We could maybe consider taking a leap, but we don't have the length of 2 to go from 1. So I do not consider that a leap would be possible if we only had 1 step or 1 step ahead of us. But after I take that step, we would reach the top of our staircase. Same thing here at this one. We could only take a step. From this 2, we could either take a step or a leap. Step would give us 1, leap would give us 0, and then from this, we could only take a step, which would give us 0. And here, this would give us 1, 2, 3, 4, 5 distinct ways. To climb this staircase when we can either take a step or a leap at each moment. Now, I want to talk briefly about this recursive solution and how it's going to relate to this sort of tree diagram here. And I just want to highlight that by just looking at the single of 4. So again, I could either take a step or a leap. If we step, we'll go to 3. If we leap, we'll go to 2. Now, if I think about this 3, that would be as if we were starting a new problem. The staircase had 3 steps ahead of us, and we either could take that step or that leap. The trick will come when we come to something like this 2. So this 2, we could step, we could leap, 1, 0, and then I could just take a step, would be 0. So we want to design a recursive function, but if I was here at this 1 and we stepped, well, we reached the top of the staircase, and we would count that as a distinct way, and we would want to make sure that we were able to return that back as we went back through our functions. Same here with this leap. We would want to make sure that when we see this 2, that it would be able to know that, hey, I have found 1, 2 distinct ways. Okay, I think that's enough for the surface. Let's jump back to, well, not jump back to, let's go into a coding environment and figure this out. Okay, we are in a coding environment. I went ahead and set up a file, step_recursive py. We're in Python, and I wanted to demonstrate how I think about going about solving this problem, but still with that specific example in mind. So we were talking about 4 steps ahead of us. We'll use n for that, and I want to use a step list to hold all of the options of steps that we could possibly take. In this one, we could either take a step length of 1, the step, or 2 for the leap. And let's set up a print to print out a function, and I want to call that function climb stairs. It's good enough. And def. And we will go ahead and pass this function n the number of steps ahead of us, as well as our step list. Now what I want to use to keep track of the distinct ways is going to be result. Very original there. And we'll go ahead and return that. And back to this print, climb stairs, and we'll pass it the number of steps as well as the step list. I like highlighting things because I tend to misspell things sometimes, which gives me errors, but I think everything's good. So let's run this. Python step recursive.py, and we should get an output just of 0. So let's see if we get that. Good enough. So let's move forward and talk about these decisions. So anytime that we're presented with steps ahead of us, just like in the tree diagram back at the surface, we have some choices to take steps based on our step list. So let's set up a for loop for, let's say, step length in step list. And 3 things could happen, but really only 2 of them are we really going to be interested in. We could have if n minus our step length, it could be greater than 0. Elif n minus step length could be exactly equal to 0. And the third would be n minus step length is less than 0. Now, the first one, n minus step length being greater than 0, that would indicate that after this current step length that we took, we could still possibly take steps in order to potentially reach the top of our staircase. So in that situation, we need to call our climb stairs again, keeping in mind that any distinct ways that this new function would find, we need to return that back and be able to capture that. And what we're capturing distinct ways was in result. So we'll set result equal to whatever our current result is, plus, and then we'll call the function again. And we're not going to pass it n, we're going to pass it n minus step length, as well as our step list. Okay? Oh, forgot the underscore. There we go. Now for here, if n minus step length is exactly equal to 0, equal, that would indicate that we have found a distinct way, that we've reached the top of our staircase, and we need to increase our result by 1. So we'll take whatever our current result is, set that equal to, we'll set result equal to whatever our current result is plus 1. And finally, we could have it where n minus step length is less than 0. Now again, just like I mentioned down at the surface, in this situation, we really don't care about it. We're not going to do anything there, so I'll just get rid of that. That'll be fine. And I think this should all be good. Let's just maybe make a few double checks. Okay, I think this should work. We'll go ahead and save this, run this again. Now, we should get a result of 4. Crossing my fingers. Here we go. Oh, sorry, it should be 5. It was 5. Sorry, not 4. 4 is the length of our staircase, and the result that we should get is 5, just like we got from the staircase. Okay, now that we've done 4, I want to show you that this recursive solution is only good for relatively small numbers of n, the number of stairs ahead of us, and relatively simple step options to take. So I want to increase this just to 30, run that, and you'll see that this isn't quite as snappy as it was with just 4 steps. So let's run that. And you see there, it took a moment. It wasn't that long of a moment, but it did take a moment to calculate. Now when I increase this to 35, now we will notice quite a longer wait time. Save, run that again, and I'll roughly count here. 1, 1,000, 2, 1,000. Okay, so maybe about 6 seconds. That is forever when considering computers, okay? Took a significant amount of time to calculate that. And that is because this solution ends up being exponential, the complexity. Now next time I'll talk about that lookup solution. That one I believe is complexity is linear, and we'll go from there. Anyways, thanks for joining me for my first ever YouTube video kind of vlog thing. Hopefully you will join me next time. Until then, bye.